Unfortunately, our lecture on Friday, I'm sorry, was disrupted because of some technical issue at my end, and because of various things, I was not able to come online and inform you that there's a technical problem coming up. Anyhow, so we will continue from the lecture that happened before that, in which we had just about reached towards the end of the concept of terminal velocity from Stokes' law. So we will revise that derivation once more and mainly discuss the applications. So with that, we will finish properties of matter. We can discuss few questions and doubts in properties of matter if you have any, and then move on to the next section of physics. Okay. As I've told you before, the next section of physics is a very important one. It is oscillations and waves, which has a lot of weightage as far as JEE is concerned, JEE and boards, and also it has it's one of the fundamental aspects of physics which will require understanding even for other topics in physics. So anyhow, let's finish with the application of viscosity and Stokes' law. So what we had understood in general, that if we have any solid object, okay, of any shape and size, it does not matter. If it's moving inside a fluid with a velocity v, a fluid such that it applies viscous force in it, then the fluid will end up applying a resistive force or a drag force or a viscous force, which we can write as Fd or Fe, whatever. So this drag force or viscous force so this will always be such that it is directly proportional to velocity, but opposite in direction. And this constant of proportionality, this C, will depend on, first of all, the viscosity coefficient eta for the pair of materials. That is the fluid in which the solid is moving, that fluid's material, or what fluid that is basically, and the solid object which is moving inside the fluid. And it also depends on the size and shape of the object. Okay. And we had seen that in the special case of the object being a spherical body, for a solid, it may not be a solid sphere, but mainly the shape has to be spherical. So for a spherical body of radius r, we had seen that this constant becomes 6 pi into coefficient of viscosity into r. So the drag force basically becomes, if you write it as a vector, it is minus 6 pi eta into radius into v. We just write it in terms of magnitude, you can see that minus sign is not important there. Okay. And then based on this, we had understood the free fall of a spherical body inside a viscous fluid, considering three forces acting on it. One is the weight of the object, the other is the buoyant force that the fluid applies, and the third is the viscous force. Now the weight and buoyant force are constant forces which don't change with time, or which don't depend on the velocity or the motion of the object. However, the viscous force is the one which increases in magnitude as the velocity increases. So what happens is that the acceleration of such a body as it is in free fall starts to reduce, because as it picks up speed, the viscous force increases, and eventually it achieves what is called a steady state or terminal velocity condition, where its acceleration becomes zero. So this general property of a body in free fall inside a viscous fluid, it will be applicable for any shaped body. Okay? The only difference is for any shaped body, the value of the constant C it cannot be written so simply. You'll have to do experimental analysis of it and calculate the value of C for different types of bodies with different shapes. However, for a spherical body, we can just write that constant because we know it from the experimental analysis that was done by Stokes and his physics group at that point of time. So that's why it's called Stokes' law. Stokes was the name of a scientist. So Based on that, now we have also the formula of, Stokes law is like a combination of two things. One is this formula, the force on a spherical body, and the other is the analysis of free fall of a spherical body in a viscous fluid, and especially the formula of terminal velocity. So everything we're discussing here is part of Stokes law from the spherical body onwards. So moving ahead, and we are talking about, so this part we had done in the last lecture, so I'm going through it a little fast. Okay, so free fall of a spherical body, and this time we will take a solid sphere. We'll assume its density is uniform, okay, in a viscous fluid. So in this we will take the radius of the sphere as r. We'll take the density of the material of the sphere as rho s, let's say, because it's the solid. Okay, and for the fluid we'll consider the density as rho l, and we will consider the coefficient of viscosity for this pair of materials as eta. Okay. Of course, we have acceleration due to gravity. So as the solid sphere is released from rest, okay, initially, just at the moment it is released from rest, its initial velocity being 0 at t equal to 0. What we had seen is that there are only two forces acting on it, weight and buoyant force. Because even though the liquid has viscosity, but its velocity is 0. So the viscous force is 0. So there is mg and buoyant force. So it sets off with an acceleration a0, but initial velocity of 0. But as we analyze for a later instant of time, what we realize is that its acceleration is reduced because of the viscous force which has come in now. So alongside with these two other forces, buoyant force and weight, now there is also the additional viscous force, the drag force or whatever. We have buoyant force, weight, and drag force. So the acceleration A at some time t has become less than a0, the initial acceleration, and by now it's picked up the speed v. So at time t equal to t, we can see that we have mg minus buoyant force minus viscous force is equal to m into a. Okay. Whereas at t equal to 0, we had just mg minus buoyant force is equal to m a0. Okay. So you can see that mg minus viscous force we can directly write as apparent weight. Okay. So it's basically density of the solid minus density of the liquid into volume into g, and on the other side m is density of the solid into v into a, where this v is obviously 4 by 3 pi r cube. So we can directly see from this equation that the initial acceleration is like 1 minus ratio of the densities into g. So for example, if the density of the liquid is negligible compared to the density of the solid, then the initial acceleration is almost k0, is almost g. But now in this equation, we can see we'll get this term will again be difference of densities into volume into g. Okay. Minus now viscous force, that's our variable thing. This is our viscous force. That is equal to density of solid into volume, that is the mass, into dv by dt. So we get this kind of a relation that dv by dt, the instantaneous acceleration, is when you divide this, you see this first term is a0 minus some kind of a factor. Now I'll call that factor beta into v. Okay. Or we can also write it as alpha minus beta into v, whatever. Okay. So here you can see a0 or that factor is basically 1 minus density of solid upon density of liquid upon density of solid. Okay. So I'm just repeating this so that you also learn to write all this very fast. Okay. Whereas this factor beta is our 6 pi eta divided by 6 pi eta r, sorry. I pointed that out, that there is also factor of r over here. Okay, so this is 6 pi eta r divided by density of solid into volume. So that will become 6 pi eta r divided by 4 by 3 pi r cube into density of solid. So as you can see, that will become 9 by 2 eta upon r square into density of solid. Okay, so this factor is like this. So this becomes our important equation only. And as we had seen last time, the first thing that we analyze in this equation is not integration for velocity as a function of time, but just understanding the terminal velocity condition. That is, that when the velocity becomes constant, at that point of time, dv by dt should become zero. So the terminal velocity comes by just solving this equation only for the condition that the left-hand side of dv by dt has become zero. Okay. So if you just want to go through the details of this section once more, just do that quickly. You have it in last time's notes, but just go through the steps. If there's any doubt, let me know. I will discuss with you. Yes, Jagannath, I'm coming to the integration of the last part. And yes, Devansh, I'm just going through this section again carefully. We have done this derivation last time, so it's fine. All right, so now let's proceed from this. So the first thing that we can see from here is that at terminal velocity condition, so the term terminal velocity condition means that like it's reached the final velocity. That means the velocity is not changing anymore. So it's reached a sort of a steady state when the velocity, which is the terminal velocity, has become uniform. Okay, and the acceleration has become zero. Okay. So this is the terminal velocity condition. So when this happens, the acceleration is zero. So that means a naught minus beta into terminal velocity should be zero. So that means the terminal velocity by formula is a naught upon beta. So that is 1 minus this ratio of densities into g divided by this factor that we had over here, which was 9 by 2 into coefficient of viscosity divided by r square into density of the solid. So we see that the formula of terminal velocity that we get from here becomes density of solid minus density of liquid multiplied by a factor of 2 by 9 into r square g divided by a factor of coefficient of viscosity. So this is a rather sort of lengthy formula to remember. So what I would suggest is instead of trying to memorize the formula, just remember the concept that at v equal to terminal velocity, the concept is that the acceleration should be zero. So that means mg minus buoyant force minus this should be zero. So mg minus buoyant force should be equal to the drag force. So that's it. Now this is very easy to derive very quickly. So just this concept you remember that when the velocity becomes terminal velocity, this condition is satisfied. So then it's very easy to understand the formula. Okay. So especially at JEE Mains level question, you will get questions which are kind of just application of the formula, and you should not struggle to recall the formula and things. Okay. So okay, now that's one thing. Now the other thing is we can also use this equation above here to find velocity as a function of time. Like as it's going from the initial state where it's just dropped from rest till it reaches this steady state or terminal velocity condition, how the velocity is changing with respect to time and how the acceleration is changing with respect to time. So in other words, the whole kinematics of the motion. It's a straight line motion, but it's a straight line motion with non-uniform acceleration. In fact, it's having a diminished acceleration. That is, the acceleration is reducing with time and eventually becoming zero. So now next thing let's understand is the velocity as a function of time. That also I think we had seen just about towards the end in the last lecture. that we get that exponential function which comes by integrating this. We have this where these factors of the. So let's do this integration once more in detail. So cross multiply to bring all the terms with v on this side and keep the dt on that side. Okay. So now we can integrate this. Now at t equal to 0, it started from rest. At t equal to t, the velocity became v. So now we are just using the standard integration for maths, that integration of 1 by x is ln x. So integration of 1 upon a linear function becomes, by substitution, ln of that linear function divided by the coefficient of x plus c. So here the coefficient of x is minus beta. So this becomes ln of a naught minus beta v with a minus 1 by beta. Now, okay. On that we'll put the limits from v equal to 0 initially to v equal to v. The other side we just have time, right? Now substitute the limits. So minus ln of a naught minus plus ln of a naught minus beta v. Just carry this beta that side, so it will become this. So ln of a naught minus beta v divided by a naught is equal to beta t. Now take the exponential on both the sides. Oh, sorry, I've taken the.
Oh, okay.
I think this plus minus will get interchanged. So just a minute. The upper limit is v, so the upper limit is minus of ln a naught minus beta v, and the lower limit is minus plus ln a naught. So this will. So I have this now. Ln of a naught upon a naught minus beta v is equal to beta t. So now I can take log exponential on both sides, and I can just use a trick here that I want to solve for v, so I want to bring v in the numerator. So I'll just invert both the terms, left hand side and right hand side. I'll invert them. So this will become e raised power minus beta t, and then I'll cross multiply. So then finally, just resolving this, we'll get it as now. Recall the fact that this term e naught upon beta, that is actually the terminal velocity. That is that factor of 2 by 9
Rho
r square into
G by
different density upon beta, g also, this kind of term. Okay, so the velocity as a function of time becomes like this: terminal velocity into 1 minus e raised by some negative exponential factor of time, where understand that terminal velocity is given by this formula. And beta is of course this factor. So they are both constants. Okay, so let's analyze this a bit further. So one thing you can see over here is that the quantity beta, it has dimension of time inverse, because the quantity beta into t is basically a dimensionless term. What in language of dimensions you say is, having dimensions of 0, m to the power 0, l to the power 0, t to the power 0, like that. That you can check out also, because beta's value is this. So you can see that dimension of beta is dimension of, so I'm not doing this, but you can verify it yourself later that this will come out to be 1 upon time. Now the other thing is that at t equal to 1 by beta, which is like a constant value in time, v becomes this terminal velocity into 1 minus e raised by minus 1, or it becomes approximately 0.693 times this. Because e is approximately 2.7. So 1 minus e raised by minus 1 is approximately 1 minus, it's about 0.69. Sorry, not 0.693, 0.639, or 63%. So of course, actually before this, let's start with this, that b is equal to 0 at t equal to 0. That you can see from the formula, that zero. Okay. But at this particular value of time, what happens is it reaches about 63% of its terminal velocity. The velocity reaches this value at this value of time. And finally, as t tends to infinity, okay, v tends to become equal to terminal velocity. Now, this equation is a little misleading, and I'll show you how it is misleading also. this tends to suggest that it takes infinite amount of time for an object in free fall like this to reach steady state. But what I'll show you is that saying that it's infinite amount of time is actually a bit of a misleading term, because what we mean by t tending to infinite is that it's a large value of time compared to the quantity 1 by beta. Okay. It doesn't necessarily mean that it's like millions of hours or something like that. It can be just a few seconds also. It just depends on what the value of that beta is, or rather what the value of 1 by beta is. So I'll show you that with an example. So practically what this means is that t is large compared to 1 by beta. This factor of 1 by beta becomes important. Okay. And by large, actually, we don't even mean like extremely large. We just mean that
at greater rate.
yes, like multiple of the factor 1 by beta. Okay. So for example, at t equal to, let's say, 10 times 1 by beta. Remember, 1 by beta is the time when it's reached 63% of the terminal velocity. So, depending on the values of all these parameters, the coefficient of viscosity, the size of the object, that is the radius and all these things, also the difference in densities, how much difference in density between the solid and the liquid, depending on all these factors, let's say beta is just a few seconds. So then 10 times a few seconds is not that large an amount of time. It's not really like it's infinite time. But compared to 1 by beta, it will be large enough. We'll see what will happen at this kind of time. Your v will become terminal velocity into 1 minus e raised power minus 10, because that factor is beta into t, and I've taken this. Okay. So like
Okay, it will be nearly equal to 1.
You can see that this factor is like this quite small. No? This is like that e 1 upon e raised power 10 is how much? It's like even if you take a very approximate value of e like 3, it's very small. No? This is very small compared to 1. So for all practical purposes, this will be like 0.9999 something, like that kind of value of terminal velocity. It's very close to terminal velocity. So what we mean by t tending to infinity is actually this. That it's a large multiple, it's a largest multiple. It doesn't have to be thousands or millions of times of 1 by beta. It can just be a few times 1 by beta, like 10 times or 15 times or even 7 or 8 times. It will be very, very close to the terminal velocity. So it will be almost equal to terminal velocity. So that will be reflected when we, in the graph also, in the pattern of the graph, when we draw v as a function of time. So exponential graphs have that kind of behavior, that they reach the asymptote condition pretty soon. You must have heard of the term asymptote in coordinate geometry or calculus.
Yes,
also. There are hyperbolic asymptotes. There are trigonometric asymptotes like tan x graph.
Tan theta. Yes, tan and cot.
Cosec, cot, all of these have. But like that, exponential graphs are also asymptotic, and the exponential function is such that it reaches the asymptotic condition pretty fast. If it's a decaying condition, then it decays very fast. If it's a growing condition, it grows very fast, like that. Okay, so Jagannath, I hope this point is clear now, the meaning of this term. You asking about the fourth point in the note or the earlier part? Okay, so which part? The third one? See, all this now, this data that I've, the conditions that I've written. Okay. See, this is all all these observations are coming from this formula here. You see this formula, na? V as a function of time. In this formula, what you can observe is that V is equal to some constant, which is basically what? It has the dimensions of velocity into some factor. So if you look at this equation dimensionally, V on the left hand side is a velocity. Vt on the right hand side is also a constant which has the dimension of velocity. So that means this bracket has to be dimensionless. So obviously this number 1 here is dimensionless. It's a numerical constant. And this exponential factor is also a numerical constant. It should not have any dimension. So whenever we raise e to some power, it cannot have any unit or dimension. That has to be a pure number. So beta into t has to be dimensionless. The term beta into t, this has to be just a number. It should not have any dimension. It should not have any unit. So that's why beta has to have the dimension of 1 by time. Is this point clear now, Jagannath?
Yes, sir.
Okay, now the next point is that again, how we know this thing that v is 0 at t equal to 0. One was, of course, at the start of the derivation, we had put the condition. So obviously, we had derived this formula by using this limit that at t equal to 0, see, we put u equal to 0. So it's obvious that that should be the case. But now with whatever formula we've got, you can verify that also. That formula, it should be valid only if at t equal to 0, your v is 0. And you can see that that's happening. You put t equal to 0, this factor becomes 1 minus e raised power 0, which is 0. So the velocity is 0 initially. Okay. And similarly, now you put the value of t as 1 by beta. Now remember, earlier I told you that beta has the dimension of 1 upon time. It's a constant that has dimension of 1 by time, or is a constant that is expressed in like per second or per minute, something like that. So 1 by beta is a constant which is having the dimension of time. It's expressed in seconds or minutes or hours or whatever, right? So 1 by beta is a constant which is in the unit of time. So at t equal to that constant value of time, what is the value of v? So that we are getting by substituting t as 1 by beta. Okay. And the explanation for that is here. Okay. And similarly, t tending to infinity, this exponential factor will become e raised by minus infinity. No? So it's tending to 0. So that's how the v is tending to vt, or the terminal speed. Hope all these points are clear now. Okay, very good, Jagannath. Okay. Okay, so especially at your JEE Advanced type of level of questions, then you can get something which is more like a kinematics question based on this kind of velocity profile, okay, or on the terminal velocity condition and the general properties of free fall of a solid object inside a viscous fluid, which has that kind of equation, that acceleration is equal to some constant minus some linear term of v. But before that, from this we can also derive the acceleration of the particle. So the last point over here, what about the rate of change of velocity or the acceleration? So that is, if you differentiate this term, which we got earlier, just apply the normal chain rule thing, you'll see you'll get Vt into the derivative of this factor. Now this factor's derivative, one's derivative is 0, minus e raised power minus beta t, but into minus beta, because the coefficient of t in the numerator is minus beta. So this derivative will become minus minus plus, okay, divided into e raised power minus beta. Now notice that terminal velocity into beta is nothing but the initial acceleration. Nothing but a naught, because remember a naught was, Vt was equal to terminal velocity upon beta. We had this thing.
Okay.
So this factor, or even when you substitute, you can see that this will come out to be that thing we had written. The difference of 1 minus the density of liquid by solid into g. This thing. So this term is like this. So the acceleration also has this kind of a pattern, that the acceleration is that initial value of acceleration into an exponential decaying factor. Like the velocity is the terminal velocity into 1 minus exponential decaying factor, whereas the acceleration is directly the initial acceleration into exponential decaying factor. So here you can see that as t tends to infinity, the acceleration tends to 0. But at t equal to 0, the acceleration is equal to 0. Okay? And at t equal to 1 by beta, that important factor that we discussed, okay, the acceleration becomes a naught e raised power minus 1, which is approximately 0.37 times a naught. So the acceleration decays or reduces from a naught to about approximately 37% of a naught in t equal to 1 by beta, which has a dimension of time. Okay, and it decays to 0 for t, greater than few times 1 by beta, like t equal to 10 by beta or something like this. Okay. So it almost tends to 0 by then, or it reaches the terminal velocity condition. Okay, so Jagannath and Rakshit, both of you, just you can go through this and write all this down. Okay. Uh, Jagannath, actually, empirical value isn't like you just put E as approximately 2.7 and you'll get that value. It's actually from calculation, not from empirical. Is like when experimental data is used. But yeah, I mean, this whole final formula is empirical only because it comes from Stokes law, and Stokes law is an empirical formula. That whole factor of 6 pi eta r, that has come from experimental analysis. So in that sense, it's not wrong to say that it's empirical. But So here to here, no, this step to this step, we are just getting that by substituting E as approximately 2.7. As you know, E is an irrational number, non-recurring, non-terminating decimal, but you can approximate it to first place of decimal as 2.7. So finally, to understand this like more from a visual perspective, you can, if you look at the graphical analysis of that function, how V is varying with time, and side by side, you also look at the analysis of how the slope of that graph, because the slope of velocity versus time graph is nothing but acceleration, how that is varying with time. Actually, what we are discussing in this part, it is actually a part of kinematics. It's like a 1D motion which has that kind of variable acceleration, where the acceleration is varying with time such that it's linear with respect to the velocity, linearly decreasing with respect to velocity. It's that kind of situation. Anyhow, so the velocity as a function of time, its graph will have this kind of a shape. So it's asymptotically approaching this kind of graph. You will see in number of other places in physics also, like much later in nuclear physics you will see. Then very soon you will be seeing in a chapter called capacitors, which is like an application of electrostatics, charging of a capacitor. That's the equation you see. So the velocity, it very rapidly rises to almost the terminal velocity, but it starts from zero. And this is where that factor becomes important, that in one value of time called 1 by beta, it reaches 63% of that terminal velocity. So now imagine the slope of this graph, or just draw the graph on the basis of graphical analysis of the formula also, either way, and you'll understand how the acceleration varies with time. The acceleration varies with time according to A naught into e raised power minus beta t. So this is a decaying kind of exponential graph. This also decays rather rapidly and almost tends to zero. So it's an asymptote, but it approaches that asymptotic condition rather fast because it's an exponential function compared to something else like a hyperbolic function or trigonometric asymptotes. This is very rapidly decaying. So this like that same amount of time, 1 by beta, the acceleration has become something like about 1/3 the initial acceleration, 37%. Whereas if you also see the graph of acceleration versus velocity, that one is a straight line graph. This one. So when the velocity was zero at t equal to 0, the acceleration was a naught. When the velocity becomes terminal velocity, the acceleration becomes e. So v is equal to that e naught minus beta v kind of condition. So a is equal to minus a. Or as a differential equation, this becomes dv by dt. So whenever we have this kind of a condition that the rate of change of v with respect to time is linearly decreasing with v, then always we will have this kind of kinematics. Okay? That it will be a decaying acceleration and the velocity will be initially increasing at a rapid rate. You can see the slope of this graph. Okay, but eventually the velocity reaches a terminal condition and the slope of the graph becomes zero. So this whole analysis is important from that point of view also, not just for Stokes law application, but whenever in kinematics we have a situation like this. This is how it behaves. Okay. Okay, people. So hope this is all clear. Okay, couple of doubts. Let me see. Acha, go back to the previous note. Yeah, I'll go back. Even now. You'll probably see all this together. Okay, so what is very important here is not just this particular Stokes law application and formulate, but you remember this pattern very much, like a kinematics problem, 1D motion, where the acceleration has this behavior that A is equal to some constant minus some constant into V, or the acceleration versus velocity graph looks like this, a straight line with a negative slope. So the moment that happens, we should understand that this is how our velocity will be behaving with time, and this is how our acceleration will be behaving with time. Okay, so Jagannath, this is done, I hope. Okay, so now let's move on to some typical type of numerical problems. Okay. For example, we can have something that doesn't even exactly involve Stokes' law. It's more like an application of the general concept of viscous force or drag force, which is again that type we have discussed above. Okay, so a solid object is dropped inside a fluid such from rest. Okay. And begins its free fall at t equal to 0. Okay. If its initial acceleration is, let us say, 8 meters per second square, g is equal to 10 meters per second square, and its velocity is 20 meters per second at t equal to 30 seconds, and eventually reaches a terminal velocity of vt equal to 40 meters per second. So we have to find out the relative density of the solid with respect to, no, actually no, we'll leave this out for the moment. We'll come back to this relative density. Initially, what we'll calculate is we'll find the acceleration E at t equal to 30 seconds. Then secondly, we'll find out the velocity v at t equal to 60 seconds. t equal to 90 seconds, then we'll find out both A and B as functions of time. Okay. So for all these parts, we don't even have to assume that it's a spherical body, but the fluid is viscous, of course. So otherwise, there's no question of terminal velocity. If the fluid did not have viscosity, then it would go on accelerating forever. So it would not reach a terminal velocity condition. Okay, so just try this out, people. We'll discuss in a moment. Okay. So basically, you have to just use the equations that we have been discussing about above. Okay. This is exactly that situation. The kinematics will be such that it has that decaying acceleration, and therefore speed which is increasing, but such that the speed is increasing in a way that the slope of the VT graph is gradually decaying. So it eventually becomes a flat line and it reaches the terminal velocity. So it has to be that exponential kind of function. Okay, so basically, see what you have to do here is you have to just fit this data that is given to us, all this data that initial acceleration is this much, the velocity is this much at this time. You have to fit this data into that kind of pattern. Okay, so we know that free fall inside a viscous fluid will always involve this, that your net force will be equal to weight minus buoyancy minus drag force. Okay. So it will always be a situation where dv by dt is going to be the initial acceleration minus some factor into v, where your initial acceleration will be nothing but mg minus buoyant force divided by the mass. So it is 1 minus density of solid, sorry, density of liquid divided by density of solid into g. And your beta will actually be like your, coefficient of the drag force divided by mass of the body. Where drag force is having a magnitude of c into b. So if it is a solid sphere, then if it's a solid sphere, then your beta has that standard value that we had seen. Otherwise, it has some other value, okay, but it's a similar kind of term with similar dimensions and similar relationship with coefficient of viscosity and all that.
Sir, R square provides.
Sorry, what was your question, beta, again? Come again.
Sir, वो बीटा का वैल्यू R square by rho s होगा, the density of solid.
हाँ, rho of this solid, so not g. Okay, so now, but see, we don't really need to use this. We just need to use this equation with the data given above. So what was the data given above? It is given to us that A naught is equal to 8 meters per second square, whereas G was 10 meters per second square. So that is obviously showing us that this factor is 0.2. And it was also given that V is equal to, what was it, 20 meters per second at t equal to 30 seconds. Okay. And terminal velocity was equal to 40 meters per second. Okay. Now, before that, we also understand that this, what it implies, that v is going to be terminal velocity into 1 minus e raised power minus beta t, and e is going to be a naught into e raised power minus beta. So the moment we have this condition, it implies these two equations. We are going to make use of this. So now this data has to be fitted into these equations. Okay. So fitting this only, I've got, okay, so acceleration as a function of time will become 8 into e raised power some exponential factor like this, where I need to find out the value of beta, of course. Okay. And velocity as a function of time will become 40 into 1 minus e raised power minus beta t. Now this data we will use and we'll find the value of beta. So 20 meters per second is the velocity, but at what time? 30 seconds. So from this we will get the value of beta. Okay. So once you got the value of beta, then we got the two things we required. We got v as a function of time, and we got a as a function of time. So now basically you have to solve this maths equation using ln, because you will get e raised power minus 30 beta as some numerical factor. So take ln of that equation on both the sides and solve it for beta, and tell me how much you get beta, and tell me in the units also that you get beta. Remember, beta should have unit of 1 upon time. अच्छा, समझ वो formula से आ रहा है ना? See, in this equation you just substitute g as 10 and a naught as 8. So you get that now? This factor is coming by substituting these two values in this equation, that a naught is equal to this factor. Oh yes, Shikhar, we can use that also. That's correct.
Sir,
Yes.
sir, for beta, can we use A naught upon terminal velocity?
We can, but see here. Okay, let's wait a minute. Let me just change
Sir,
the question.
because
Wait.
yeah,
Let me just
terminal
change the
velocity is
question.
given.
Is given. So let's here in the question. Now this is not given. Okay, we have to find out A naught also. We have to find the initial acceleration also. And from that, we have to find out the acceleration as a function of time. Okay. So both the things are unknown. Okay, so we'll proceed in the manner that I said earlier now. But using the value of that relationship now, that terminal velocity is the one you just told me, that A naught upon beta is terminal velocity. So using that, we will get the value of A naught now. So here, even A naught is unknown for us. Okay. This one. Yeah, otherwise we could have used that very effectively. So question would have become very fast. Okay. But so then extra data would have been given in the question. But here extra data is not given. Okay, we are using this. Yeah, Samar, that is correct. We'll get some different value of A naught by L. So we'll find that out also. Don't worry. Okay.
Sir, beta का value 0.02 आ रहा है.
Okay, a unit.
Second.
Second inverse beta.
हाँ, second inverse. Sorry, sir.
Okay, correct. Good. Okay, so Rakshit, you have wanted to see the question again, or okay. Okay, so let's come to this now. So this when we solve, we'll get, just take the 40 this side. So we'll get 1 by 2 is equal to 1 minus e raised power minus 30 beta. Okay, so that tells us that e raised power minus 30 beta is half, or if we invert this, we'll say e raised power 30 beta is 2. So now we can take ln on both sides. So 30 times beta is ln of 2. Okay, and ln2, as you might have seen in chemistry, a lot of calculations are based on this, is approximately 0.693. ln2 is actually 2.303 times log 2. That is log 2 to the base 10. So it is into 0.3010. So that is 2.69. So anyhow, so this beta, now this 30 is seconds, remember, whereas this ln2 is dimensionless. So it is ln2 upon this 30, which is in seconds. So it is approximately 0.693 divided by 30 second inverse. So that is becoming 0.0231, correct? This is the value you got, Peter?
Yes, sir.
Okay. Okay, so people, hope all of you are clear with this value of beta that we got now. Okay. So now from this we can see that terminal velocity was given to us as 40 meters per second, and beta is in proper units 0.0231 second inverse. So automatically our initial acceleration, which is terminal velocity into beta, will come in meters per second square, right? So कितना हो जाएगा? It will be oh, it's almost coming as much as I had predicted. Anyway, so 9.2 आ रहा है ना? 0.231 into 4. It's slightly more, but right. So this is the initial acceleration I'm getting. So now from these things I know everything. I know velocity as a function of time is 40 meters per second into this factor. Okay. I know acceleration as a function of time is into this factor. So I can just more conveniently I can just write this as beta t and put the value of beta below. These are the functions where beta is equal to second inverse, right? So I hope this is clear to all of you.
Yes, sir.
Okay, now the rest of the things are just substitution. Okay. Now we want to find, the second thing was we wanted to find V and A at t equal to I mean A at 30 seconds. V already we had 60 and 90 seconds. So this too we already know that V at 30 seconds was 20 meters per second. But now we can also see what is V at 60 seconds. Okay. So try to do the calculation yourself once. Okay. It should come out to be 10 meters per second. Okay. Oh, sorry, it should come out to be 30 meters per second. It should increase by a factor of 10. And then V at 90 will come out to be 35 meters per second. And similarly, the acceleration initially was this much. So the acceleration at 30 seconds will come out to be a naught by 2 or 4.62 meters per second square. And the acceleration at 90 seconds, oh, sorry, the acceleration at 30 seconds will come out to be this. The acceleration at 60 seconds will come out to be a naught by 4. And the acceleration at 90 seconds will come out to be a naught by 8. These will form a geometric progression. And I'll explain to you later why that's happening. When you do the calculation, you'll understand yourself actually why they're following a geometric progression.
So how did you get the acceleration?
Yeah, sorry, I think one of you asked a question. I missed that little while back.
Ha, sir. How did you get the 30-second and onward
I'll explain
acceleration?
how we got this. See, so what is happening now? You can see here that our terminal velocity is 40 meters per second, and our velocity at 30 was becoming 20 meters per second. Okay, so now given this relation that, sorry, given this relation that v at any instant is terminal velocity into 1 minus e raised power minus beta t. So if you substitute this information here, you get the idea that when t is equal to 30 seconds, at that point of time, this factor of e raised power minus bt is how much? It's half, right? Because it's 1 minus half, this factor. This is clear,
sir.
no?
Yes,
So
sir.
now see what is happening. So when t is equal to 60 seconds, this factor will become e raised power minus 60 beta, which is basically e raised power minus 30 beta 2 times. So it's half ka square. So it's 1 by 4. Okay. So like that, when t is 90 seconds, e raised power minus 90 beta. Okay. Sorry, I meant this to be 30 beta. Okay. So this is becoming now 1 by 2 to the power 3. Got it now?
Yes, sir.
So that's why it's following the geometrical progression. So you can see that now your velocity, how it will be going at 30 seconds, your v and also your a is basically what? A is equal to a naught e raised power minus beta t. So at this point of time, your v will become half of terminal velocity and your a will become half of a naught. Okay, but at this time, your v will become terminal velocity into 1 minus 1 by, sorry, 1 minus, so 1 minus 1 by 4, so 3/4 of terminal velocity, whereas your a will become a naught by 4. Okay, and at this point of time, your v will become terminal velocity into 1 minus 1 by 8, right? Whereas your a will become a naught by 8. Follow that kind of pattern. Just substitute in this formula and answer. Okay, so if we analyze this information graph wise, also it gives us something quite interesting actually. See both the graphs simultaneously. So our velocity versus time graph and our acceleration versus time graph. So this is following this kind of pattern. So it exponentially reaches that asymptote value of 40. But we can also see that it reached 20 at this time, which was 30 seconds. Okay. So interestingly, it now reaches this midpoint of 30, but at a time of double of this. Okay. And then it reaches the midpoint of 30 and 40, that is 35, after another 30 seconds. So that is the nature of exponential graph. In equal intervals of time, this changes by an equal factor. It's a curvature like that. It's the exponential of logarithmic mathematics actually. This comes up in number of places in physics. Okay. So for example, we have a chapter coming up of sound later. We will see that when we talk about the decibel scale of loudness of sound, this also becomes an important factor over here. How our hearing system perceives sound, that also becomes. Again, it's becoming exactly A0 by 2 at 30 seconds. Then it's becoming exactly half of this interval because this one is decaying. It's becoming A0 by 4 at 60. And then again, this interval is half. And then, for example, at another 30 seconds or 120 seconds total time period, it will become 1 by 16 of A0 like that. Whereas this will become like that. 37.5 and like that. So just through this question, I'm showing you that behavior of exponential functions or the inverse of exponential is logarithmic. So logarithmic mathematics has this kind of behavior. Okay, so that brings us to the absolute last part of viscosity. Something called spelling I struggle with. Poiseuille's equation. So Poiscuill.
Puzzles.
Think I have got the spelling right. You can check later with the textbook.
Yes, sir. It's
Might be single L or might be double L. I'm not sure. So this gives us the equation for laminar flow of a viscous fluid through a cylindrical pipe. If it was not a viscous flow, then it would have been a steady flow, and we have already understood steady flow in hydrodynamics chapter. Okay, but here we are talking about a viscous fluid, so that concept will not be applicable. The hydrodynamics concepts of continuity equation and Bernoulli's equation will not be applicable anymore. Okay. So it turns out that if you want to push through a viscous fluid through a cylindrical pipe at a certain volume rate of flow, then because viscosity will be dissipating kinetic energy, it will be doing negative work on the system. So to keep it going through that pipe at a uniform volume rate, we'll have to apply a pressure difference across the pipe manually or through some external mechanism. Otherwise, the volume flow rate will start to decrease. Okay. So that is one important thing. And the other thing is that the flow of the liquid will be laminar in nature. So that means there will be a velocity gradient. The velocity will not be uniform. So this is the axis of the cylinder. We'll see that because of viscous forces, there'll be a radial pressure gradient that the fluid will have. So first of all, if the cylindrical pipe is of length L and radius R, okay, and we are pushing through liquid, volume flow rate, the liquid is, let's say, delta V by delta T. Or in the original equation, this is given by the symbol Q, but actually it's nothing but volume flow rate. So the volume flow rate will be directly proportional to the pressure difference. So if liquid is flowing in this direction, we'll have to create a pressure difference across this. Okay, and it will be equal to a relation that we write like this: pressure difference divided by something called viscous resistance. So now you can compare this to heat flow or flow of current. To maintain a constant flow rate, we need to overcome viscous resistance. Here the resistance is because of drag forces of viscosity. So we need to overcome that by creating the pressure difference. Just like to maintain uniform heat current, we need to overcome the thermal resistance by creating temperature difference. Or to overcome electrical resistance in a conductor, we need to create a potential difference. So that kind of relation. Okay, so the volume flow rate depends on the pressure difference. And it depends on viscous resistance. So this viscous resistance is now given by quite a ghastly formula, and we will derive that formula just a bit. 8 times the coefficient of viscosity into L
L into Q.
divided by, sorry, what was that, beta?
Sir, L into Q, na?
What into Q, beta?
Sir, 8 eta LQ upon
No,
pi.
not LQ, beta. L divided by pi r to the power 4.
Okay.
Okay, we'll derive this. Okay, it's 8 eta L. L is not cube in the numerator, huh? It is,
Yes, sir.
sorry, not 8 pi, 8 eta. Pi is in the denominator. Coefficient of viscosity divided by pi r to the power 4. That's the formula. Now we'll see the derivation of this also, though the derivation is not part of your board syllabus. So that is one thing, but also another interesting thing about it is that the liquid will have, because the fluid will be in laminar flow, such that it has a radial pressure, radial velocity gradient. So radial gradient means rate of change with respect to radial distance from the axis. Okay, so let me explain that in this diagram what it means. It means that if the liquid which is flowing at the axis, think of like one line of liquid molecules moving along the axis, they are moving at some speed v naught. Then as you go away from the axis, the speed of the liquid molecules is decreasing. So think of this three-dimensionally. Okay, I'm just drawing it in 2 dimensions, but it's varying with the radial distance, like this. Okay. So v is a function of r. Okay, so that dv by dr, that is your radial volume gradient, radial velocity gradient. Okay, so let's look at both the things, the velocity gradient as well as the how we get the formula for that viscous resistance.
Can you scroll up for one?
Yeah.
Thanks.
So the velocity is varying with radial distance as we discussed before. So now imagine you have a cylindrical shell of liquid. Okay, which is at a radial distance r from this axis. So it's this distance r. So this is moving at some velocity v. Okay. Now just above it, there is another shell, or you can say just outside of it, there's another cylindrical shell of liquid, and that's moving at a slightly slower speed, v minus dv.
Yes.
Whereas just inside of it, there's another shell that's moving at a faster speed. So what is happening? The outer surface of this shell, now it will experience viscous force because of that one. It will experience viscous force like this. Okay. So that viscous force will have to be balanced by a force due to pressure difference. Okay. So if like this was my, so this is my pipe. So we are considering a section of the pipe which is of length L. So here actually I made like a diagram of a section of fluid within the pipe, like a thin cylindrical shell of thickness dr, radius r. So this, which is moving like this. So this thin cylindrical shell of fluid that is going to experience viscous force on its outer surface. So remember the formula for viscous force in laminar flow of liquid. The viscous force is equal to coefficient of viscosity into the area. Now that surface area will be how much? It will be 2 pi r L. This is the surface area of contact. Okay. Into magnitude of the velocity gradient. Okay. Earlier we had seen this formula that viscous force is equal to eta into A into magnitude of velocity gradient like this, where the velocity was varying with one of the dimensions like this. So that formula we are again applying over here. So on a surface of area A, the viscous force was like this. So same kind of formula. But here it's a radial velocity gradient and the surface area is the curved surface area of the shell. So it's this much. Okay. So now imagine, see, that if this shell is of liquid is moving at a uniform speed of v, then this viscous force has to be overcome by force due to pressure difference. Okay. So if the force on this side due to pressure is P1 into whatever area, the force from that side has to be P2 into that same amount of area. Okay. And this has to maintain, I mean, this has to have zero acceleration. It's having a velocity gradient radially, but each layer is moving at uniform velocity with respect to time. That's the only way the volume rate will be uniform. Okay. So this is like, you know, V is a function of R, okay, but V is constant in time because our volume flow rate delta V by delta T is uniform.
Sir,
Yes.
can you please explain this pressure and viscous force relation again?
Yeah, pressure and viscous force, I haven't explained yet. I'm coming to that. Viscous force relation is clear. This one, this formula is clear. No?
Yes, sir.
Okay. So now see what is happening. This whole shell of liquid is having zero acceleration. So this is like a FBD of the shell. No? So because acceleration is zero, so net force on it must be zero. So the force due to pressure, that is P1 minus P2 into area from both the sides, has to balance this viscous force. Now it's clear, no?
Yes, sir.
So, okay. So this pressure difference into the cross-sectional area of that, which is the pi r square, is going to be equal to 2 pi r L into dV by dr. Okay. So ultimately, we are seeing that dV by dr is coming out to be how much? P1 minus P2 into R upon 2L. Correct. This is what the velocity gradient is. This is the radial velocity gradient. But only one thing is there here. There will be an extra minus sign, okay? Because this is mod of dV by dt. So now we understand that since V is maximum at R equal to 0, that is at the axis, okay, and minimum, that is V is equal to 0 at the outer edge, that is R equal to capital R. So therefore, V is decreasing with respect to R. So mod of dV by dr is actually minus of dV by dr. So the proper relation for the velocity gradient or radial velocity gradient is that minus dV by dr is equal to this kind of a constant into R. Okay. So what this shows us that the velocity gradient is directly proportional to R. So that means V should be what kind of a function? It should be a quadratic function. And that's what we'll get when we integrate this. So anyhow, I'll just leave you to analyze this part for a bit. Note down the key parts of the derivation up to here. Then we will see how we'll relate the volume rate of flow with the velocity gradient. And from that, finally, the volume rate of flow with the pressure difference. And from that, we will derive that formula that viscous resistance is 8 eta L divided by pi r to the power 4, but pi capital R to the power 4.
There should be a eta in the RHS.
There should be an eta. Na? I've missed out an eta somewhere. Yeah, after this, I forgot the eta, na? Where the drag force I have substituted. Yeah, so it's eta into this. Okay, so we just add an eta here. So the eta will come in the denominator. Yes. Is okay now?
Yes.
तो लास्ट में dv by dt होगा कि dv by dr होगा?
dV by dr, radial. dV by dr. It's the radial pressure gradient, radial velocity gradient. Okay. So actually, just relate this with a diagram once more, then we'll come back to this. Jagannath and Shikhar, you wanted to scroll up to this point or further up?
So further up.
Okay, just a minute. Starting from here?
No, sir, that radial velocity gradient will do.
Okay, okay.
So I wanted the part after that RV value.
Okay, so this is fine now?
Yes, sir.
Okay. now next thing, once we got the velocity gradient, so you can see that this factor that I've written in the bracket before r, this is a constant. No? So that's why we'll understand that v will come out to be an r square kind of term, but with an, I mean, a minus r square kind of term. So when we integrate this, next we'll see that this factor is just a constant, but so it can come outside the integration. And the maximum speed which is there at the central axis is for r equal to 0. So at r equal to 0, the speed of that line of molecules or that small volume elements you can think is v0. And as you reach the outer circumference, the speed becomes 0. It's almost at rest because the pipeline's inner surface's viscosity is preventing the liquid from moving over there. So it's like, concentric shells of cylindrical shells of liquid scraping against each other in such a way that the outermost one is almost at rest against the inner surface of the pipe, whereas the innermost one, which is like the thin cylinder at the center or like the thin line at the center, is going at the maximum speed. So this shows us that we'll get here we'll get minus v0, and here we'll get
So it will be plus v0, no?
sorry, plus v0. Here we'll get this into r square by 2. Yeah. So there is this relation between these.
Sir, only R square, right?
Only R
I
square.
have taken, yeah. That should be 2 over here. This one. So P0 is this sort of a factor. P1 minus P2 into R square upon 4 eta L. Okay. So from this we can also see that alternately, if I integrate this from V0 to V on this side, on the other side from R equal to 0 to R equal to R, then we get this kind of relation that so invert this and we'll get this relation that V is equal to V0 into 1 minus R square by capital R square. So this is our V as a function of R, and this is V0 in terms of this. So we have already used this over here. Okay, so basically what we've done is we found the speed of the central axis as how it depends on P1 minus P2, that pressure difference, and other factors like radius, eta, and all that. And then we've also seen how the radial velocity, I mean the velocity at a radial distance r, is a function of that V0. It's a quadratic function. So if you plot that relation, you will see that this is a parabolic profile. This velocity profile will be parabolic in shape. At a radial distance r, V is varying like this. So now we have to just finally understand how much volume is flowing through that pipe per unit time, given that we now understand the velocity as a function of the radial distance. Okay. So next thing, for volume flow rate Q or delta V by delta T, because the velocity across the cross section is not uniform, we have to basically get this volume rate by integrating this velocity of flow with respect to area across the cross section. Had it been a uniform speed like it was in hydrodynamics, it was just V into A, speed of flow into area of cross section. But here we have to integrate. But luckily for us, that integration is very simple, because if you look at the cross section of the pipe, it's a circular cross section and the velocity is varying radially. So we don't really have to worry too much about the integration part. So what we'll do is, at a radius r, I mean, basically we are looking at the cross section of that thin cylindrical shell that we had drawn earlier. So let's say if liquid is going into the cross section of the paper or into the plane of the paper here, or the screen here, then in this shell, at every point the velocity vector will be going into the plane. Okay. So if its thickness is dr, so this dA is the cross section of a ring, a differential ring of radius r and thickness dr. So dA is 2 pi r dr, and the speed of flow for every particle going through that ring, that imaginary ring, is that factor that we just derived. So now we can see that the volume rate of flow is integration V dA. So that is two pi r dr from r equal to 0 to r equal to capital R. So when we do this derivation, this integration, so 2 pi v naught comes outside, okay, and we have r minus r cubed by r squared dr integrated from 0 to capital R. So this will give us r squared by 2 minus r to the power 4 by 4 r squared. On this we have to put the limits from 0 to capital R. This factor like this, or V naught into pi r squared divided by 2. Now remember what V naught was earlier. V naught was the pressure difference into divided by 4 eta L, okay, into r squared divided by 4 eta L. Substitute that here. So our volume flow rate is or basically pressure difference divided by viscous resistance, where viscous resistance is this factor. So basically this is a nice practice of integration and this kind of things, but other than that, it's direct formula based in terms of questions. So just like if you want to push a block on a rough surface at a constant velocity, you have to continuously apply a force on it because you have to overcome the friction. So like that, if you want to push a viscous fluid through a cylindrical pipe at a uniform volume rate, you have to continuously apply a pressure difference. Whereas had it been an ideal fluid, okay, which is non-viscous, therefore, you don't need a pressure difference for uniform volume flow rate. In a horizontal pipe, that is, of course. If the pipe is at a gradient or is vertical, you still need to apply pressure difference. Okay, people, so that brings us to a conclusion of this entire section of physics of properties of matter. Okay. So we have one more session this week. We'll keep some time aside in that session for discussion of doubts and questions, but we will also move on to oscillations, or that chapter is also called simple harmonic motion. So actually simple harmonic motion is a special case of oscillation. Oscillation is a whole type of motion, a whole periodic type of motion, and simple harmonic motion is one category of oscillations. However, the chapter can be interchangeably called either thing. So coming up is that very important chapter of simple harmonic motion oscillations. Okay, that's it for today's session, people. Thanks for attending. Wish you all the best and have a nice day.
Sir,
Yes.
sir, in one of the HC Verma questions, it was given Poisson's ratio. Sir, what is that?
Poisson's ratio. Yeah, I'll explain to you in the next class, but just remind me. Poisson's ratio is the ratio of the rate at which the when there is longitudinal strain created in an object, its diameter will also change. If you have a solid cylindrical object, so its diameter also changes. You understanding, no?
Yes, sir.
So if an object has a natural length L and a natural diameter D, so when we now expand it to elongate it to an elongated length of L plus delta L, its diameter will tend to decrease. Okay, so this ratio of the rate at which the diameter changes, or the fractional change in diameter divided by the fractional change in length with a minus sign, okay, that is called the Poisson's ratio. So it's given by the symbol sigma. So that is also material property, just like Young's modulus or Bulk's modulus, or all these things are. So we'll discuss about it once. Okay.
Okay, sir.
Thank you, sir. Bye, sir.
Okay.
Thank
bye.
you, sir. Bye.
Thank you, sir. Bye, sir.
Okay.
So,
Bye.
sir,
Yeah. Yeah, Jagannath.
so could you show the equation below radial velocity gradient for 1 second?
Yeah.
I'll take the screenshot.
Yeah. Okay. This one.
No, sir. Little more up.
This one.
Little more up. Yes, that's it. That's it. Since V is max at the force.
Okay. Okay, Jagannath, run then.
Yes, sir. Thank you.
Okay. Okay.
Bye.